Let's talk about how the atomic mass table was developed in the 19th century. Berzelius, a Swedish chemist, in the early 19th century gave us our 1 to 2 letter symbol for the elements that we use today. He published 43 elemental atomic masses in 1818 based on his method. More than that, he determined the percent composition of about 2,000 chemical compounds. Just imagine how much time that took him during the long Swedish winters. He came up with a method of equivalent mass and used that. The equivalent mass of an element is defined as the amount of that element that will react with 8 grams of oxygen or its equivalent, say in hydrogen. So for example, he found that in silver oxide, to make it, you had to have 13.5 grams of silver reacting with 1 gram of oxygen. The equivalent mass then is what would have reacted with 8 grams of oxygen, and 13.5 times 8 is 108. If you compare that with the periodic table mass of silver, you see he was very, very close to what we now accept. Franklin came up about 30 years later with the notion of valence that we still use today. And it asks the question, how many atoms does an atom we'll just call X combine with? Well, it's defined by the number of hydrogens that it combines with or replaces. He assigned a negative valence if it combines with hydrogen. So for instance, hydrogen reacts with chlorine with oxygen and forms the ammonia compound with nitrogen. Valence is assigned a positive number if it replaces hydrogen. So for instance, zinc reacts with hydrochloric acid to form hydrogen gas. Sodium reacts with water to form hydrogen gas. All of those things we know are metals, and they have positive valences. It's exactly the same system we use today. The valence method of atomic mass then uses both of what we just looked at. The atomic mass is assigned to be the product of its valence and its equivalent mass. For instance, zinc has a valence of +2. You know that from your work in the first year. Its equivalent mass is 32.6. When you multiply them together, you get 65.2. Very, very close to the mass that we accept today for zinc. Not of all of those, however, on the table that you see on this slide are really close. For instance, you see phosphorus is. Can you find some that are not very close to the mass that we assign these days? If you didn't find one real quickly, try carbon, which he's assigned a 6, but today we know as 12. Now Dulong and Petit, many years earlier, had come up with another method of finding atomic mass. They found that the product of specific heat and their atomic mass would be about 6. So for instance, copper has a specific heat of 0.0932 calories per gram. That's how they measured things back then. Remember, a calorie is the amount of heat that changes the temperature of 1 gram of water by 1 degree Celsius. The atomic mass then is 6 divided by the specific heat, or 64.4. Compare that again to what we call the atomic mass today, and it's very close. Aluminum does the same kind of calculation and gives us a 27.6 gram. Why is this very, very close? Well, I advance the notion that since aluminum has a smaller atomic mass than copper, 1 gram of aluminum will have more moles of atoms than copper does, and so it's going to take in more heat. It'll have a higher specific heat capacity than the same number of grams of copper. Now the problems are that the methods that we've looked at were close, but they did not converge on one or another, and there are some big errors. So Dulong and Petit had a 10% error for sulfur, and we saw that problem we ran into in a previous slide with carbon. Moreover, Dulong and Petit could not figure out an atomic mass for liquids and gases. And some elements, of course, we know have multiple valences, like iron has a +2 and a +3. So how do you solve this problem of non-convergence of the methods? Well, they called a conference. The conference was held at Karlsruhe in what we now call Germany, and the idea was to come to a consensus and come out with an atomic mass table. They had every important chemist in the world, and they elected Jean Dumas, who, as you know, invented the Dumas method for figuring molecular mass of liquids. But the conference did not produce agreement. In fact, it made things worse, and it broke up in confusion. But as they left, one of the participants gave each of them a pamphlet by Cannizzaro, and they went home and they read it. Cannizzaro's method is called A Sketch of a Course of Chemical Philosophy, and Lothar Meyer liked it. He used it, and others began to use it. You see, what had happened is Avogadro's hypothesis had been pretty well forgotten or pushed aside for, about 40 years. And Cannizzaro used his hypothesis to get relative molecular masses of gases, and then worked to find the smallest mass of an element in several compounds that might be made with that element, and assign this the relative atomic mass. I'll show you on this next slide the calculations that he published, which you're not going to have to explain, but please notice the regularity of 3 in the column on those several different compounds of the halogens of chlorine and iodine. When that 3 came up, we had a regularity. I can explain it a lot more easily with the next slide. If you consider 3 compounds of hydrogen, water, ammonia, and methane, and you take their density and you multiply the density by the percent of hydrogen by mass, you get numbers, the product, and if you look at those, you see that they are in the ratio of 2 to 3 to 4. We can see also that that's how he came up with formulas. See, the problem is, if you know the formula of a compound, you can figure out its empirical mass, the atomic mass. Or if you know the atomic mass, you can figure out the formula. But what he was trying to do was get down to the simplest, the smallest of those numbers, which for water is 2 hydrogens per oxygen, for ammonia is 3 hydrogens per nitrogen, and for methane is 4 hydrogens per carbon. This was electrifying to chemistry. They were finally able to get a handle on atomic masses. The numbers in the last column we see are the number of hydrogen atoms in each molecule of these 3 substances. The next step, once Cannizzaro had the number of atoms of an element in a compound, he could then use the several tables to converge on the best atomic mass of those that have been proposed. For example, as you know from your experiment, you found that the molecular mass of that compound of carbon and oxygen that they called fixed air, that we now call carbon dioxide because we know the formula, it had a mass in your experiment somewhere between 40 and 45. Really close work shows it to be 44. Now, that's in comparison with O2, oxygen, which is 32. Well, if the oxygen is subtracted from the carbon dioxide, fixed air, we get 44 minus 32, or 12. And that's how I came up with the best atomic mass for carbon. Lothar Meyer said, after he read the pamphlet, that the scales fell from his eyes, and he could now predict chemical compounds. He could predict the masses of compounds that would be formed in a chemical reaction. That gave us chemical engineering. That gave us stoichiometry. And it gave Meyer and Mendeleev in Russia the data that they needed to produce their periodic tables. Both of them published periodic tables. Mendeleev was working under a great disability. He was Russian. He was writing in German, publishing in a German publication. Mayr was a German, writing in German, publishing in German publications. And so, why did Mendeleev prevail? The answer to that question is going to have to depend on your recollection of the history of the periodic table. But I think if you'll look back in your notes or look in the textbook, you'll find why Mendeleev prevailed despite all of the disadvantages. What did he do that Lothar Mayr did not do?